Coming down from alpine mountain heights of quantum crystallography down to the plain routine analysis of X-ray experimental results, the approach I want to show you is known for at least 70 years. The software will be non-modified routine refinement programs. Here is an example I want to show you. Common organic molecule with hermetic and aliphatic fragments collected with reasonably high resolution. It shows residual density peaks at all bonds in hermetic fragment, also lone pairs, and it shows, of course, alerts and unnecessary high R factor. A very common approach will be cut off to 0.8 angstrom, so you have better R factor, no warnings, but we can do better. Now, where residual density is coming from? It can come from atomic movement, rotation, vibration, that is often described as disorder. It can come from electron density deviations from independent atom model, from covalent bonds, lone pairs, ions. Of course, it can come from data collection errors and limitations of procedure or data processing errors. It seems that in our case, the dominant is number 2, electron density. Let's try to apply correction to this sort of bias. Now, caution, we have ordinary data set, so we should not even try multiple refinement. In 1950s, Rosalind Franklin published one-page paper in Nature, where she stated that for quantitative description of X-ray diffraction from graphite, one must take into account bonding electrons located exactly midway between two carbon atoms. Interestingly, all previous observations of electron density was based on diamond data and were mistaken because in fact it was all Renninger effect. It seemed that this paper is the first correct observation of covalent bond density in X-ray crystallography. However, it was completely dismissed and never cited by charge density community, never by Coppens, never by Hirschfeld. Again, here we have electron density that lies exactly between two carbon atoms. So how can we treat this bond scattering based on what we know? Simple approximation of residual electron density would be Gaussian in three-dimensional space. And for me, a transform of Gaussian will be another Gaussian, in this case in reciprocal space. This was used by Brill in 1960 when he treated diamond, and later was used by Coppens when he was studying residual density in organic molecules. Much later, the same approach was applied by Afonin and a large team, treating abnormalities in protein molecules. As a result, bond scattering is a part of high-resolution model in Phoenix Refine. There were plenty of other applications of so-called virtual atoms or dummy atoms. As an example, virtual atoms are embedded in MoPro. How can we use bond and lone scattering using IM software? Let's look at Cromer-Mann scattering factor. It's 9 numbers, 5 of them showing number of electrons, and we cannot change number of electrons by our scattering center. Also, the result is multiplied by the Debye-Wheeler factor. That again is one more Gaussian. It's natural to put only one number, and we are putting this number in position of F prime. So we do not change number of electrons, and this is anomalous scattering. for real is a cheating way to get around changing number of electrons. We name the electron in our scattering factor. If you use OLEX, you need to put helium or something like that, because it will not accept new names. Your algorithm would be solve and refine structure as usual. Check if residual positive density is located on covalent bonds. If not, stop. Name already refined real atoms as part 1. Add scattering center as an atom in SVAT's directory. Calculate position of interatomic scattering centers, bonds. Simple approximation is to place them exactly between 2 of carbon-nitrogen atoms. Same for lone pairs. Fix their coordinates. Assign new bond atoms block as part 2. And refine use res file. If desired, several further adjustments can be done. You free occupancy factor for each scattering center, free isotropic parameter, can add CH bonds, and so on. Graphic user interface, the best will be Shellxel. OLEX2 is acceptable, but any typo can kill your work. YANA should be fine as well. So what we do, we have our usual carbon and hydrogen for our biphenyl. Now we are writing our SVAT line here with some arbitrary number around 0.2 for our dummy atom, and mention it in your unit parameter. You name it helium in OLEX2. You name your existing atoms as part 1. You apply part 2 for your new scattering center. And you have variable occupancy. And you have variable Debye-Wheeler parameters. So 2 parameters. 1/2 here is coming from inversion center. The result will be dramatic drop in R factor from 5.9 to 3.6. Improvement of bond precision, better weighing scheme in Shellx, smaller thermal parameters. Hirschfeld atom refinement can give you even better on the price of lengthy calculations. Now, if you do several different crystals of the same compound, you'll of course have some deviation between them, and we can compare these numbers. Improving beyond 0.005 doesn't make much sense to me. What we have with residual density is dramatically decreased. We have much lower density. We do not see anything on bonds. This effect drops down with resolution. If we artificially make lower resolution, both IAM and IAM plus bond model will have lower effectors. But the difference will stay almost the same, which is reasonable. If you hide your mistake, it is still with you. So anyway, we have serious improvement of our experiment. This stays with us for any aromatic compound. We have around 50 to 40% improvement when we apply scattering center to our aromatic compounds. If you are coming to compound we started with, it's not only aromatic but also aliphatic residues where this effect is less prominent, but still have nice improvement of our data. Of course, Hirschfeld atomic refinement is even better, but not too much. With our approach, we can use disorder groups here and there, and doesn't affect the result. Now, what happens if we apply this approach to benchmark datasets collected at very high quality? Here I am using the rubberin dataset that was mentioned in the original paper for hard refinement in OLEX2. So full Hansen-Coppens will give you a factor of 2.45, hard 2.62, recent calculation with NOSFERA2 gives 256. IAM gives 418, but application of scattering center drops it to 273. And even if we'll forget to do CH bonds, we are at 284. So we still have most of improvement with our very simple model. Another benchmark data set, this is coming from Göttingen group. IM model is at 298. IM plus scattering center 221. Hart and NOSFERA2 are of course better, but again it prices very complicated calculation. Most of the effect is done with the simplest correction. If you'll just take a random structure from IUCR data, what will happen? We still have improvement in our model. Flag parameter is staying the same. Surprisingly, NOS2 did not give sufficiently good data in this particular case, but otherwise, of course, it's a vast improvement. So it works for practically any random structure. Interesting example is a lead, where we have sulfur, and we have very nice improvement with IM plus bonds if we include hydrogen atoms. Hart, NOSFERA2, and MOPRO are given essentially the same numbers, but much better precision in bonds. The same effect is visible in ionic crystals with transition metal complexes. NOSFERA2 is far more efficient in this case, but still most of the effect is visible in IM bonds approach, even with no hydrogen atom correction. So, summary. We have a simple tool for residual density cleanup. A very simple approach for removing covalent bond in lone-paired residual density. We are using no pre-calculated parameters from DFT calculations or other sources. We use the same software, Shell's OLEX Refine YANO. It can encourage you to collect data to higher resolution. When do the correction, you can stop at any level, make all bonds different, or keep all bonds the same at the same time. You can apply bond scattering to a fragment of structure, for example, a aromatic fragment. In most cases, CH bonds practically do not affect the outcome. No, you cannot calculate reallocation of hydrogen atoms. For this, you need to change scattering factors for at least hydrogen atoms, but better for others. It's a separate story, but there are better methods for treating hydrogens. It will not work with heavy atoms. This restriction is the same for others. It will not work with low-quality data. You cannot correct a bad data set with a good model. If correction doesn't work, maybe something wrong with your data. After correction on bond and lone pair scattering, R factor and geometry are better. Now it's possible to come back to residual density map. Pay attention to other sources of error and bias. Say atomic moment disorder, data collection error and limitations, data processing error and limitations. Example. No disorder with 10% occupancy or lower should be ever considered before the bond's density correction is applied, because your possible residual peaks are simply peaks from charge density. Before doing hydrogen disorder, it's a good idea to remove residual density, not to put hydrogen when you have a lone pair. And at last, If you want to do real charge density, you almost certainly need better data than your ordering dataset.